Welcome to another episode of Jones Math Ed Problem Solving with Dr. Jones and Lucy. Today we're talking about the greatest common factor. So if I ask you, Lucy, to find the greatest common factor, I need to say like the greatest common factor of what? So if I say find the greatest common factor of two numbers like 45 and 63, I'm going to write GCF for the greatest common factor, and then I'm going to put those numbers in parentheses.
Okay.
How do you do that? What's a way that you do that?
Well, there are several ways. So I'm going to start with way number one. So first you take the numbers and you split them. So obviously there's 1 and the number.
When you say you split them, what do you mean you split them?
We split them into their factors.
Okay, so we're listing the factors.
Yes,
okay.
We are listing the factors. Now we ask ourselves, once we get the 1 in the number, we ask ourselves, is this divisible by 2? And for both 45 and 63, it is not divisible by 2.
Okay.
So 2 is not a factor.
All right.
So we go to 3. Is 3 a factor of 45? And the answer is yes.
Okay.
It is 3 and 15.
Okay.
And for 63, is it divisible by 3? Yes, it is. It is 3 and 21.
Okay.
Then we go to 4, and since it's not divisible by 2, it's not divisible by 4.
Okay.
5, for 45, it is. It is 5 and 9. But for 63, it isn't divisible by 5.
Okay.
So we go to 6. Since it wasn't divisible by 2, neither of them are going to be divisible by 6.
Okay.
7, this one is not divisible by 7, but this one is. For 63, so it's 7 and 9. And we get up to 8, it's not divisible by 8 because it wasn't divisible by 2. And 2 or 4, and now we go to 9, and we've already had it. So the greatest common factor of 45 and 63 is 9.
Okay. So that's the greatest common factor. Are there other common factors?
Yes.
What are the other common factors?
3
Okay.
and 1.
All right.
But all numbers are going to have a factor of 1.
Have you ever heard of the least common factor of two numbers?
Yes.
What's the least common factor of 45 and 63?
1.
1?
Yes.
What's the least common factor
Other than 1?
of, no, I'm picking some different numbers,
Okay.
of 106 and 145. What's the least common factor of those?
Do you want me to use the same strategy?
No, I'm asking for what's the least common factor.
Okay, well.
What do you think is the least common factor? Not the greatest common factor, the least common factor.
1.
1. Why do you think people don't talk about the least common factor very much?
Because it's always going to be 1.
It's always going to be 1. That's kind of boring. Okay, so we're not really talking about the least common factor. We're talking about the greatest common factor. You said there were several ways. You numbered this as number 1. Maybe get a different color and do a different way.
All right, number 2. Yay, okay. So for way number 2, you can take the numbers 45 and 63, and you can turn them into these little tree type things.
Okay.
Okay, so 45 is divisible by
All of these numbers, right?
Yes.
Okay.
So let's start with the largest.
Okay.
5, which is prime, and 9, which can be split into 3, which is also prime, and another 3, which is also prime.
Okay.
And this can be split into 7, which is prime, and 9, which is not prime, and 3 and 3.
So you're circling the prime numbers there.
Yes.
Okay.
That means that we cannot split it up any farther.
All right.
So 45 could also be equal to 5 times 3 times 3, and 63 could also be equal to 7 times 3 times 3.
Okay. How does that help you get the greatest common factor?
Well, the greatest common factor is the one that is the same between the two.
Okay.
That is the farthest up the tree. No, the highest.
Well, maybe not necessarily, because we could make a factor tree without even having a 9 in there. Like we could say 45 is 3 times 15, and then I don't even get 9 in there. So let's look at those prime factorizations that you wrote. 5 times 3 times 3.
When you simplify this, you can get something that is very similar.
Okay, so you're writing 9s. It looks like you're writing G's there.
That's how I write my 9s.
I know that's how you write your 9s, but not everybody knows that. So if we look at what they have in common, they have 2 3s in common. And so we can take those 2 3s and say the greatest common factor of 45 and 63 is 3 times 3, or 9, because that is the factors they had in, those are the prime factors they had in common.
Yes.
Okay, let me show you another way. This is a really old way. And I want to use the calculator to do this, so we'll put that on the screen here as well. And so if I want to find the greatest common factor of, I'm going to use the same numbers because the answer I want to know the answer is 9. We're going to use this really old method. It was done by Euclid, who's from the last video that we talked about, and it's a method or an algorithm that he came up with. And so the idea of the Euclidean algorithm is, what were you going to ask me?
Do you want me to label it 3 for our third way?
Oh, please label it for the third way. Yep.
Yes.
Okay.
Okay, this one's going to take a while.
This one, we're going to need some more paper on this. Yeah, so the idea behind the Euclidean algorithm is we're going to divide 60, well, you usually pick the larger number and say it's equal to, we're going to divide by the smaller number, but this is kind of weird. I said I was going to use the calculator, but when I take 63 divided by 45, I'm going to get a whole number quotient.
With a remainder.
With a remainder. So 63 divided by 45 is, what's the quotient? How many 45s can we get out of 63?
1.
All right. And then the remainder would be
63.
63 minus 45. Whoops. And we get a remainder of 18.
18, yes.
Okay, so the way I'm going to write this here is I'm going to rearrange it. I'm going to say 63 is equal to 1 times 45, that quotient right there, plus the remainder of 18. This is still a true statement. 1 times 45 is 45, plus 18 equals 63. So that's how I'm going to write this. When I say divide, I really mean I'm going to pick a number times, I want to use a different color, 45 plus the remainder. And we already figured out that the remainder was 18.
Yes, so then...
So 63 was 1 times 45. And now Euclid's pattern says, now I'm going to take the divisor and the remainder, and I'm going to write 45 is equal to something times that remainder, 18, plus a new remainder. So can you figure out what that quotient and remainder are?
2, and the remainder of 45 minus 36 is 9.
Okay.
So then we take those
How did you know that? That looks like an A. How did you know that was a 36. Where did you get the 36 from?
8 times 2 is 6.
8 times 2 is 6.
16.
Oh, 8 times 2 is 16? Okay. So 18 times 2 is 36. Is that what you're saying in a not saying it way?
Yes.
Okay. Then we're going to keep this process going. Euclid says keep going. These remainders are going to keep getting smaller because the remainder always has to be smaller than the number you're dividing by.
And smaller, and smaller, and smaller.
So now I'm going to divide 18 by 9.
Which would give you 2.
2. And what's the remainder for that?
The remainder is 0.
0. Now Euclid says when you get to 0, that means you're done with this process. And so
Yay.
now what we do is we look at that number, that remainder right before, that 9 is a factor of 18. And since 9 is a factor of 18, 9's also a factor of 36, the 2 times 18. And 9's also a factor of 36 plus 9, which is 45. So 9's a factor of 18, 9's a factor of 45. Since 9's a factor of 18 and 9's a factor of 45, it's also a factor of 63. So the greatest common factor of 45 and 63 is 9. That's how this process works. Okay, so the reason why I wanted to show you this process is because it works out to be, it was more work here maybe than these other problems, but if I give you some big numbers,
Like,
yeah, what numbers do you want to find the greatest common factor of? You pick one, I'll pick the other one. One, 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 one. So 5 ones. Okay. And I'm going to pick a number. Could you put one more 1 in there? I would feel a lot better if you did. Okay. So 6 ones. Thank you. And I'm going to pick 6, 0, 5, 0, 4, 0, 3, 2, 1. So this gigantic number there. I would put commas in there, but it would make it kind of hard. 605 million, and you've got 111,111. So I don't want to do way 1 or way 2 with this, even though these are really good, because these numbers are huge, and I don't want to find all the factors, and I don't even want to find all the prime factors. So Euclid's way is pretty nice.
605, 04, 03, 2, 1.
Okay.
Equals
something times 111 plus a remainder. Okay, now let's get this calculator on the screen.
605, 04, 03, 2, 1 divided by.
Okay.
Is that enough ones?
So 1, 2, 3. Yeah. So how do we interpret that answer? What do we do with that? What boxes do we fill? We'll put it on the screen so we can see.
We fill that box.
With what?
With.
So the whole number part goes there. Yeah. Okay. Now how do we figure out the remainder?
Well, we multiply that by the 6 ones.
If you multiply just the answer by the 6 ones, it's going to take you back to the original number. Go ahead and hit enter.
Magic.
Okay.
That's
Whoa,
so
yikes.
wacky.
All right. So instead of that, what do we multiply?
Well.
Instead of answer times the 111111. Yep. The quotient.
Times.
Okay.
The quotient.
Times the 111. Okay. What does that give us?
I'm not just gonna.
Almost this number. So now how do we get the remainder? That's not the remainder.
Okay, 605, 04, 3, 2, 1.
Hang on. There was an extra O in there. Okay.
Minus the 604, 999, 395.
Okay. That looks like a 5. Okay, 40926. Okay, so now do you remember what Euclid said to do?
Yes, we
What?
take
Okay, and what do we divide it by?
the
Okay, and then we get some remainder there.
okay, so
Okay,
so 2.
okay, put a 2 there. All right, and then how do you figure out the remainder? Okay, is that the remainder?
No.
That's this right here. Okay. Okay, be careful with those 9s.
2, 9, 2, 5, 9.
29259. Okay. Then what do we do?
Now we take the 40926 equals something
I'm just trying to make it clear.
times 29259 plus something. Now let's solve that. Okay, so 40926 divided by 29, is that a 259? So 1.
Okay, the whole number part.
Okay, so now we just subtract.
Hang on. Now you said you knew just to subtract because why?
1 times the number is still
Oh,
the
1
number.
times that number is still the number. That's the identity property.
Equals 11667.
Okay. Can you hold your pencil a different way so you can actually write?
Fine.
Thank you. I appreciate that. And so do the viewers.
Nine equals something times 11667 plus something.
Okay.
Now let's solve for 29259 divided by 11667. So 2 times 11667 is 2334. 2334.
Okay.
Now that we have figured out that, we must subtract that from the 29259. And then we repeat.
Hang on.
Wait, that's the wrong thing.
Okay. hit divided. Is that what you meant to do?
No.
That hardly went down at all. But they are getting smaller, so this will eventually end. The problem was we just kind of picked two numbers. We need a box there for our method. Okay. Oh, that really went down. That makes me feel good.
So, 5, 7, 4, 2 equals 5, 7, 4, 2 divided by 183 equals 31.
31, that number got big. Okay.
31 times 183. Now 5, 7, 4, 2 divided by
Not divided.
minus 5, 6, 7, 3 is 69.
Okay.
Eventually, this shall end. Okay.
Okay.
So 183 equals 6. Okay, so equals 2.
Man, this is a long process. But probably not as long as finding all the factors of these numbers. Hang on. That one's 24.
To the 2.
Okay. Plus the remainder.
One, but our decimal place has gotten smaller.
Okay.
Okay. 45 minus 24. 21. Okay. 4 equals 21 plus blank.
Ooh, we're close. So, hey, what is 24 divided by 21? How many 21s can you
One.
get there? 1? What's the remainder?
3.
Okay.
Now 21. Yay.
So what's our greatest common factor of those two numbers?
7. I mean 3.
3. Yeah, the remainder right before the 0. So that's why I asked you in the beginning, I'll tell you a secret. You had 5 ones, but I knew if there were 6 ones, then the sum of the digits would be 6, which would be divisible by 3. And so I knew we could get a number that had a common factor. So I have no idea what the factors of these numbers are
Yeah,
now,
but
except for 3.
You knew it would take that long.
I did not know how long it would take because we were just making stuff up. But now I know that if we wanted to make a factor tree with this, we could divide it by 3. And we get 37037. This makes me think I can probably divide it by 37. Hey, I was right. And get 1001. I don't know if that number's prime or not. It's probably not. It's probably divisible by 9. Nope. 1001. Is it divisible by 17? No. 1001. Is it divisible by 19? No. See, so this is going to take me a long time if I do that. So I know that's prime. I know that's prime. I don't know about that one. And this number is even bigger. So thanks so much for trying that Euclidean algorithm with me.
It is, quote, unquote, wacky.
Wacky. Catchphrase. All right. Thanks, Lucy.